Okay, so I told you last time we needed to know molality for this next topic, and really the next two topics. And the first topic is freezing point depression. Turns out if you add a solute to a liquid solvent, it's going to require more energy to freeze that solvent than it would without that solute in it. Okay, that's why we add salt to water in the wintertime. If you mix in that salt with the water, then it's going to lower the freezing point of that water. The temperature is going to have to get colder outside before it will actually freeze. Okay, and we call that the freezing point depression. In other words, the original freezing point of the water was depressed, right? It was made lower because we added a solute to it. And of course, we have a formula for calculating that. And this is the freezing point depression formula. This, if you remember delta here, this Greek symbol delta, should be on the board here somewhere. Oh, right here. There's a capital delta. It means change in temp, right? Delta represents change in, so change in temp. The change in the temperature is based on negative I. I is the number of ions or molecules. The number of ions or molecules that the solute separates into when it's dissolved, okay? And this right here is this capital K, lowercase f is the freezing point depression constant. So that's just gonna be something that we will give you. It's unique depending on what the solute is, okay? So we're gonna work a problem in a moment, and I'll tell you what the freezing point depression constant is for water. We'll have to use that, but you don't have to memorize that. I'll give it to you on a test. So this is the freezing point depression constant. Depends on the solute. And then here's our friend molality. I told you that was coming back. And we also have to know the molality in order to calculate this change in temperature. Okay? Now, one thing you are going to have to remember when you do these calculations, because as you might suspect, we're going to talk about freezing in this example. Next, we're going to talk about boiling. And so you're going to have to remember at what temperature water in particular freezes and at what temperature water boils. And of course, we use typically the Celsius scale, so it's very simple. When we're using Celsius, it's 0 degrees for freezing and 100 degrees for boiling. All right, so let's do a problem and give us an opportunity to use this equation here. It's on page 276. It's example 9.7. And let's write our formula up in the corner over here. Change in T equals negative I, capital K, F, lowercase m, which represents molality. Okay, and our problem says a chemist dissolves 50 grams of MgNO3, 50 grams of MgNO3 in 275 grams of water, 275 grams of H2O. What is the freezing point of the solution? And it says that Kf for water gives us that is 1.86 degrees Celsius per molality. That's kind of a crazy unit there, but that will make sense as we do the calculations why we have that unit. Okay? So again, what are we going to need for this calculation? We're given grams here. And we're going to have to calculate molality to use in it. So we don't need grams, we need moles, right? So the first thing we're going to have to do is convert this to moles. And so we're going to need the atomic mass of MgNO3 2. And so we look up Mg, and Mg is going to be, let's see, Mg is 24.31, has an atomic mass of 24.31. AMU plus we've got two NOs, so two N's, two nitrogens. So N is 14.01, and we've got a total of 6 oxygens, so 6 times 16, and so our final, the atomic mass is 148.33, and so that means that we have 148.33 grams per mole for this particular compound. All right, so now let's convert grams here, 50 grams, to moles, because for 1 mole, we have 148.33 grams. And that gives us 0.337, 0.337 moles of Mg NO3. 2. All right, so we need that. The other thing that we need in order to calculate molality is we need the kilograms of the solvent, right? Are we given that? We're given grams of the solvent. So we're going to have to calculate that to kilograms. And so 275 grams, 1 kilogram equals 1,000 grams. And so that's 0.275 kilograms of H2O. All right, so now we should have everything that we need in order to calculate molality. So M is equal to 0.337 moles of this solute over 0.275. Where's my eraser? Sorry. 0.275 kilograms of solute for a grand total of 1.23 molality. All right, that's not the final answer to our problem though, because we were asked what is the freezing point of the solution. We want to know what the new freezing point is now that we've added this particular solute to the water, right? And so we're going to have to actually punch everything in here. Change in T then is equal to negative I. What is I? Okay, first we have to determine, is this an ionic compound right here, or is it a covalent compound? If it's an I, for everything that we've learned about, if it turns out to be a covalent compound, remember that's then you I is going to represent the number of molecules that it splits up into. For us, that's always going to be 1. So if it's a covalent compound, I will be 1. But if it's an ionic compound like this is, and you should recognize that because we know that NO3, we know Mg is a metal, we know that NO3 is a polyatomic ion. And so when we look at how many ions it splits into, when this guy splits up, you're going to have 1 Mg ion, right? And you're going to have 2 NO3 ions for a total of 3 ions, right? 1 Mg and 2 NO3s. So 3 is going to be our I there. What is Kf? Kf was given to us as, where was that? Right here, 1.86 degrees C over molality. And that's why we've got that weird unit, because the last thing we have to put in is molality, and we calculated molality to be 1.23 M, right? And so then when we multiply this out, our M's are going to cancel out. We're going to be left with degrees Celsius. And so our final answer is going to be negative 6.86 degrees Celsius, okay? So that is our new freezing point for water when we add this solute to it, okay? That's the change in T. Is that what it asked us for specifically? It says, what is the freezing point of the solution? So since it didn't ask us what is the change in temperature, since it asked us what is the new freezing point, then technically what we have to do is we have to say, well, the original freezing point was 0 degrees Celsius of water, and it lowered it 6.86. So 0 degrees Celsius minus 6.86 degrees Celsius. But we get the same thing, right? It gives us negative 6.86 degrees Celsius. So in this case here, it's actually the same. The change in T is identical to the new freezing point. When we get to the boiling point discussion, it's going to work out a little differently. But anyway, hopefully that makes sense to you. Let's move on now to talk about boiling point, not depression, because with the boiling point, it's actually going to increase. It's what we call the boiling point elevation, okay? So boiling point elevation. It's similar to what we said with the freezing point depression. If you add a solute to a solvent, then it's harder for that solvent to freeze. It takes more energy for it to freeze, and so it's going to lower the freezing point. Well, the converse of that is the boiling point elevation. And boiling point elevation. And this will make sense if you think about it for a second. Remember, why is it that that an ionic compound or a particular covalent compound will dissolve in another compound? Think about dissolving an ionic compound in a polar covalent compound. What happens? Well, the ions are pulled apart because of the attraction of the charges within the solution. Like when you dissolve salt in water, the Na and the Cl are separated because the water molecules, which carry partial charges, are attracting the negative ion and the positive ion in the NaCl. And so the point is that that attraction is stronger than what just the water molecules were towards one another when it was just those molecules by themselves. Because now the water molecules have separated and surrounded the Na and surrounded the Cl. And so my point is that the solution, actually, the bonds are stronger in the solution than it was for just the compounds by themselves, which is the whole reason the dissolving process works. Well, it should make sense then, because that attraction is now stronger, that if we add a solute to a particular liquid, then it's going to be harder for that liquid to boil. It's going to be harder for these things to be pulled apart and for the solution to actually reach its boiling point. Okay. So whereas adding a solute to a solvent will lower the freezing point of that solute, it's going to take now more energy to make the solvent boil, to separate the molecules. If the solvent, the solute has been dissolved in the solvent, and so it's actually going to raise the boiling point of it. We call that boiling point elevation. And here's our formula, very, very similar. I'm going to go ahead and put it out here so we can use it in our problem. Change in T. Our temperature is not going to go down, it's going to go up. So we don't have the negative sign in front of this one like we did for the last one. So it's change in T is I, same thing, number of ions. Kb, we had the boiling point, we had the freezing point depression constant in the last one. This, of course, is the boiling point elevation constant. Again, it's unique to the particular solvent, but I will give you that on any problems that we need it for. I times Kb, again, times molality. All right? So let's do one more problem that will give us an opportunity to use this equation, and it's on page 278, example 9.8, and it says, what is the boiling point of a solution that is made by mixing 25 grams of NaCl with 250 grams of water? 250 grams of H2O. What is the boiling point? Not what is the change in temperature, which is what this equation is going to give us, but what is the new temperature? What's the new boiling point? Okay? So we're going to, whatever we find here for change in T, we're going to add that to 100 degrees Celsius, since we're talking about water. And the Kb of water, it gives us as 0.512 degrees Celsius molality. It's the same unit as the freezing point depression constant had. All right, so we're going to have to do basically the same thing that we did before, because in order to find molality, we need moles of solute over kilograms of solvent. And so we got to convert 25 grams of NaCl to moles. So 25 grams of NaCl. We should be able to do these kind of calculations in our sleep now if we have the periodic table, and determine that 1 mole of NaCl is equal to 58.44 grams. Okay, for every 1 mole of NaCl, we have 58.44 grams. Figure that out from the atomic mass of NaCl. And so that's going to give us 0.428 moles of NaCl. All right, and the other thing we need is we need to convert this to kilograms, and again, we've done that a number of times, and so we should just be able to see that this is the same as 0.25 kilograms of H2O. All right, so let's go ahead and figure out the molality. Molality then is equal to 0.428 moles of NaCl over 0.25 kilograms of H2O, and that gives us a final molality of 1.71 mil. All right, so then the change in T is going to be equal to I. How many ions does NaCl split up into? Well, it splits up into 2, right? 1 Na ion, 1 sodium ion, and 1 chloride ion. And then our 0.512 degrees Celsius over M, which was the boiling point elevation constant that the problem gave us, times the molality, right, is the last thing we've got to put in there, and molality is, we've calculated to be 1.71, right? And so we multiply that out, and we get a final value of 1.75 degrees Celsius. Now, like I said before, that is not our final answer, because it didn't ask us what is the change in temperature if we add this much NaCl to this much water. It said, what is the new temperature? What is the boiling point of this solution if we mix this with this? So we need to say what the new boiling point is. And so the new boiling point that is going to be 1.75, it's going to be, let me just do it this way, is 100 degrees Celsius, which is the normal boiling point of water, plus this change in the boiling point, which is 1.75 degrees Celsius, for a final boiling point of 1.175 degrees Celsius. And that would be our final answer. All right? As always, let me know if you have any questions, and have a good day.